you're wondering what the theme is through all of this, it's how do the variables that we have affect the images we produce. So this one is SID, source to image receptor distance. Just for reference, you might also see terms like target to film distance, TFD, or FFD, focal spot to film distance. Those last two, TFD and FFD, mean the same thing as this, but they are older terms. So if you hear older radiographers talking about TFD or something like that, they just mean the same thing, okay? We stopped using those because they both have the word film in them, and we don't really use film anymore. It's confusing people. All right, the three things that SID can affect, it has a direct effect on exposure. This is going to be a big thing I want to talk about here today, is how SID affects exposure. This is why we standardize it to 40 and 72 inches, because minor adjustments to SID make big changes to exposure. SID affects magnification, that's geometric integrity, as well as spatial resolution, sharpness. And SID can be considered the fourth of the prime exposure factors. And if you remember, usually when we say what are your factors for a radiograph, we're meaning what's your mass and what's your KVP, right? There's three things there, MA, time, and KVP. Those are the three prime factors for exposure. The fourth is SID. The reason why we don't always say, the fourth one is because it's sort of a standard. We sort of know what the SID is. If you're telling me you're taking a hand x-ray, I know you're using 40 inches because why would you use anything else, okay? If you're taking a chest x-ray, I'm pretty sure you're using 72 inches, although that could definitely change. Anyways, SID is considered the fourth factor. So let's ask ourselves, why do we use the two distances that we typically use? Why do we have two standard distances? Okay, so first off, why 100 centimeters or 40 inches? Why is that the reasonable distance? So here's go ahead, no, please.
I know there's a term, I don't know the term exactly, but it's the maximum amount of visibility, I guess, in the x-ray determines that size, right?
Yeah, well, the way to think about it is the further your source, the longer your SID is, the better your spatial resolution will be. Okay, will always be better the further away it is. But we sort of have limits, like human level limits to what we can do, right? I could, if the source of radiation was 93 million miles away where the sun's located, right? That would produce a clearer radiograph than if it was 40 inches away, right? But the problem is that I can't reach the x-ray tube if it's where the sun is, right? It's too far away. I'm using hyperbole as a joke, but the point is we have human level limits to the distances that we can set, right? I can't put the x-ray tube higher than my ceiling because it can't get it above my ceiling, and I also can't reach it if it's up there, but in principle it would produce a clearer image, okay? Think about the focal spot, right? It has an apparent size to you, right? And if I took the focal spot and I moved it away from you, would it appear smaller or larger? Think about it. It has a size, and if I move it away from you, the size that you see, is it smaller or bigger?
Smaller.
Right. You see an airplane in the sky flying, right? And you go, there's a teeny tiny airplane in the sky. No, you go, there's a big airplane, it's just far away, right? Okay. It's the same idea, okay? The longer your distance is from the source of radiation, the clearer the images will be. So it is desirable, as they say, to use the longest feasible source to image distance, but we have human level limitations to the distance we can use, okay? So longer SIDs give us the best possible spatial resolution for all the other factors, assuming they're not changing. The minimum possible magnification, minimal patient exposure, and the widest possible field of view at the long distances. Now, why do we use 40 inches as our distance? Well, 40 inches is not 40 inches. It is a 40-inch measurement, but that's not what we did it for. We took it as the standard units in the metric system, okay? We said 1 meter, what should be the distance, right? Because it's a nice standard unit. Tabletops are usually about 1 meter high, okay? And we put the x-ray tube 1 meter above the tabletop. 39.3 inches or 40 inches, 100 centimeters above the tabletop. And that's about the maximum height that a human can feel comfortable working with the equipment and have it be as far away as it can from the patient. So we put it as far away as we can, but not so far that a human can't operate it. Okay, 1 meter above the tabletop happens to be that happy sort of distance. Basically, 2 meters from the floor, right? 6 feet and a few inches, right? Happens to be the right distance above the floor to where people are comfortable working at. And any higher than that would be uncomfortable. And any lower than that, and you're wasting distance, right? You want maximum possible distance, so put it as far away as you can, but not so far that the X-ray tech can't operate it. Okay. So 1 meter is the standard SID as a practical matter that can be vertically reached by the average radiographer, how far you can reach as an average person. I have students who can't reach that far. Okay, I've had students that were too short to reach that far. Okay, if you have that problem, here's my recommendation to you. If your table lowers, lower your table and the X-ray tube together. Okay, so lower your table 6 inches and lower your X-ray tube 6 inches, keeping your SID fixed, right? That's what we did for one of my students. You knew her. But if your table isn't lower, then you're kind of out of luck, right? You have to maintain a source to image distance. So if your table drops, you can drop your X-ray tube and bring everything down lower. That way you can operate it and reach it. But if it doesn't, like if it's fixed like this one, then maybe you have a stool to step on. That's what we actually did for that student. Is we brought a stool in, and I started having her stand on a stool, and then we were like, wait, let's be smarter than this. Let's just lower the table and the tube together. And we made new marks on the wall and on the table where her distances are so that she can keep her SID fixed, but have everything in the room be lowered to her height to be workable for her. Okay, good. So 100 centimeters is our default source to image distance, and all of our technical factors, I'm pointing at our technique chart, all of our technical factors listed on technique charts are reflecting that. They're reflecting that 40-inch distance as the distance we're working with. Now, why a different distance for the upright bucky? You know, why do we do things at 40 inches when we're working on the tabletop? And typically we're working at 72 inches or 40 inches. If those of you that have done upright radiography, you know we sort of use both distances. But with the upright bucky, we have the advantage that our rooms are usually kind of long, and now the X-ray tube pointed that way, right? It can be operated at human height, but be a long distance from the bucky tray, right? So 180 centimeters happen to be this sort of magic distance to where an average X-ray tech can simultaneously reach the patient and wall bucky as well as the X-ray tube. Okay, so it's long enough to give us longer source to image distance, improving image quality, but not so long that I'd have to do something here and then like run across the room, make a change here, and then run back to the wall, right? An average tech can pretty much touch this and this at the same time without moving too far. Okay, that's why we chose 72 inches as our distance. Now, some facilities will have a dedicated chest unit, a dedicated chest radiography unit that might have a much, much longer SID, and it's locked, it's fixed. 244 centimeters or 96 inches is that distance. But anyways, it is variable potentially, but the two standards are 40 and 72 inches for good reason. Remember, the longer your SID is, let's get the highlighter, the longer your SID is, the better your spatial resolution is, the less magnified you are, the lower the patient's exposure is, and the wider your field of view is. All of those things improve when you lengthen the SID. So when we have upright stuff, it is better for us to have a longer SID than a shorter SID because we can, and it helps improve all of these components. So let's start to take these one at a time. Let's take spatial resolution first. How is spatial resolution affected by source to image distance? I need to 2 seconds. Oh, there it is. Okay, good. Okay. My watch decided to run out of batteries on me today, so I just wanted to make sure what time we were at. Okay. All right, so effect on spatial resolution. A reminder, spatial resolution is synonymous with the word sharpness, okay? When you think spatial resolution, think sharpness. When you think sharpness, think spatial resolution. So here's the idea. Remember, and this, I'm just going to keep coming back to this, the size of the spot where the x-rays come from, the focal spot, affects detail. And it affects detail in the following way. If the focal spot size is fixed, not going to change, if you bring it closer to the object and image receptor, as shown in this image, okay, the penumbral blur will be bigger. Okay, the blurry edge to the body part will be bigger. If you take that same focal spot and move it further away from the object and image receptor together, move it further away, keep the image receptor and object fixed, further away, the size of your penumbral blur will be smaller. You increase sharpness when you increase distance, okay? And that's because as we increase distance, the blurred edge to our anatomy gets narrower, okay, sharper, clearer.
When you increase sharpness, when you increase
Distance. Sharpness increases, spatial resolution increases with increases in distance. Yeah. So that is to say, the longer your distance, the better your sharpness. The sharper, clearer your images are. The opposite of that is, the closer your distance, the shorter your SID, the blurrier your images are. That can actually be demonstrated like super duper easily, okay? I usually like to play with flashlights to show this, right? So just quickly, lights off in the room. I have a shadow cast in my hand. I'll make it distorted so you can kind of see the shadow. As I move in close, you notice the hand gets bigger. We're not worrying about this magnification right now. We're focusing on spatial resolution. As I move my flashlight in close, what do you notice to the edge of the finger? Blurrier. And as I move my flashlight away, ignoring magnification, the edge of my finger is going to get clearer and clearer and clearer, sharper and sharper and sharper. The penumbral blur gets smaller the further my flashlight was moved away. The same things happen for an X-ray tube. If you're an X-ray tech student and you haven't turned on a flashlight and played with shadows yet, you need to, okay? Everything that shadows do with a flashlight, the X-ray tube does with body parts, okay? It's the same things happening, okay? Sharpness, magnification, exposure even, right? The flashlight is brighter on my hand when it's closer and dimmer when it's further away. All of the same things happen because guess what? Visible light is the same kind of thing as X-rays are. They're both electromagnetic radiation, so it shouldn't surprise you that they sort of work the same, right? Some properties are different, but not the ones that we're trying to demonstrate. All the things that we want to demonstrate with like geometrical integrity, all of that remains the same. Okay. Everyone okay with the fact that longer SIDs make things sharper?
yes.
Okay, and the thing that changes to change sharpness is penumbra. Penumbra is the blurry edge to the body parts. This next slide should help a little bit. So this thing is called a resolution template. It's basically made of sheets of lead foil that are thick and then get subsequently thinner and thinner and thinner, okay? And depending on your spatial resolution for whatever factors you have, focal spot size, distances that you're using, you will be able to see, there will be a point where the apparent difference between black, white goes away, okay? With higher spatial resolution, you'll be able to see further down on this template, okay? With poorer spatial resolution, you'll be stopped a little higher on the template. So going from top to bottom, from big lines to little lines, the better your spatial resolution is, the further down here you can look and still see separate black and white lines. So if you look at image A, the arrows showing here, this is the sort of the furthest point down that they're saying we can tell the difference between black and white lines before they blur together. A was done at a 60 centimeter SID, and B was done at a 100 centimeter SID. B was done at a further distance. B has better spatial resolution. I can see further down on here before the lines start to blur together. And they're showing us the arrow representing the spot where they say the lines begin to blur together. Okay? Don't worry so much about this line pair per millimeter thing actually describing quantitatively the spatial resolution. That's not so important. What is most important to take away from this is the relative change in spatial resolution. Spatial resolution improved at a longer distance, image B, and was worse at a shorter distance, image A. That's the idea, relative differences. Okay. The next is the effect of SID on magnification. So, to be clear, spatial resolution deals primarily with penumbra, the blurry edge to the body part, okay? Magnification is going to be dealing with primarily this thing called umbra. Umbra is the actual part that you're casting a shadow of. So like when I cast a shadow of my hand, right, there was the shadow of my hand and then the blurry edge to the shadow, right? Umbra is the shadow. Penumbra is the blurry edge to the shadow.
Oh,
okay.
that's where I got one of my answers wrong.
Okay, good. I like little light bulb moments help. So if you look at image A here, right? Image A has a focal spot here, an object, and an image receptor, okay? And all they've done here is they've drawn straight lines from the focal spot through the object to the edge of the object to the image receptor, okay? And what we see is if the focal spot is close, then those lines that we draw are going to spread out and make a shadow that's larger, much larger than the actual object, okay? If instead, let's just put these on screen together. If instead the source is very far away, then as the lines come down, they don't spread as much and the shadow is smaller, okay? Longer distances make for less magnification because they make for smaller penumbral shadows, okay? The longer your distance, the smaller your umbral shadow, the shorter your distance, the wider your umbral shadow. That is the same exact thing as doing this, right? Long distance, shadow cast in my hand. Short distance, hand gets bigger. Okay, exact same thing. The umbral shadow is larger when I'm close and smaller when I'm far away. Okay, shown here is exactly what the flashlight does. So this can be shown on a radiograph. Remember last time when the X-ray machine broke, a couple times ago when the X-ray machine broke, I showed you guys those two hand radiographs, right? One magnified and one not magnified, yeah? This is the same exact thing, but done with a coin, okay? This is a flat coin that was placed 4 inches above the image receptor. So it was on a sponge 4 inches above the receptor. And image A was done with a 40-inch SID, this one. Image B was done with a 20-inch SID, that's this one. Image B was closer, so the shadow, the umbra, the shape of the object was larger. When possible, use the maximum feasible source to image distance.
Do we not have, maybe you said this multiple times before, but I wasn't listening. Do we not have more detail when the image is larger?
You might be able to achieve greater detail, but you will have a larger penumbra with a larger image. So if you
the edges of it will be less defined and less useful.
yeah, but you can trick yourself into saying it's got more detail because it looks bigger.
Right. So the optimal SID at a distance, and then with digital, we have things that can enlarge the picture.
Yeah, because we can just zoom in.
Adjust the image for the physician.
Right, we can just zoom in. So the takeaway from all of this is you want the longest possible SID. Okay, so for whatever exam you're doing, you want the longest feasible SID, and in the next set of notes, I'm going to talk about OID, object to image distance. So this is, because if you notice, right, when we look at this, there's a focal spot, there's an image receptor down here, there's a distance between them, yeah, that's the SID. but there's also an object and its relationship distance to the image receptor. That's OID. That's the subject of the next set of notes we're working on.
So better image and move on.
Yes.
And adjust the image for them.
Yes. So the next and last thing I want to get to with this is going to take us a minute here. I cannot overstate how important this thing is. So this is going to be what the SID's effect on exposure is, and this is a law called the inverse square law. It's like one of the main formulas you'll have to know as an X-ray tech. You should be able to pluck this out of memory, okay? So here's the idea. X-rays, as well as all visible light, but X-rays travel in straight lines, and they spread out as they travel through space, okay? Covering an increasing area with less intensity as they move away. Okay, so you can imagine, having a light bulb, right? And you're able to stop time. So you have a light bulb and you can stop time. Okay, so you take your light bulb, you turn it on. Okay, a split second, you turn the light bulb on, and light doesn't move infinitely fast; it moves at a speed, right? So you turn your light bulb on, and the light moves some distance away from the light bulb, and you pause time, and then you admire the space that the light has covered, the area that the light has covered in that time, okay? All of the light that you emitted from that light bulb at that moment in time will be within some area, yeah? Then you start time again, and the light will move further away, covering a larger area, okay? The same amount of light that covered that small area will now cover a much larger area. That means for any given spot, any given square centimeter of area along that imaginary sphere, there will be less light intensity than a moment before that, okay? As the light moves away from the light bulb, it spreads out, okay? It said in another way, I can shine the light at my hand and it's very bright on my hand, and as I move it away from my hand, notice the light beam spreads out, and then if I were to just be here, if I were to measure the light intensity on my palm, right? The light intensity is high now, right? It's kind of actually warm right now on my hand, right? And as I back away, that same amount of light now spreads over a much larger area. If I measured the beam intensity, the brightness of my flashlight at distance 1, and then compared it to double that distance, I would find that the light intensity at double the distance was 4 times less. Okay, this is the inverse square law. So here we're going to use some graphs and we're going to show a formula, but they say here, as the SID is doubled from 30 centimeters to 60 centimeters, the area covered by the X-ray beam increases from 4 squares of area to 16 squares of area. So if you look, focal spot's up top. Distance 1 is 30 inches. Distance 2 is 30 centimeters versus 60 centimeters, just 2 different distances. And at distance 1, the light field covers 4 squares, okay? If each of these squares was a centimeter, then we can say the light field covers 4 square centimeters, okay? Now let the light keep going to double that distance. At double that distance, that same amount of light that was packed into 4 squares now covers 16 squares, an area 4 times larger, okay? So the same amount of light now covering an area 4 times larger. That means for each square, the amount of intensity measured will be 1/4 as much as at the first set of squares, okay? Taking the same amount of light and covering 4 times more squares, so the light is 1/4 as intense at each square. The concentration of X-rays at plane D compared to plane C will be 1/4. The correct way to word this is the concentration of X-rays is inversely proportional to the square of the distance. We'll put a formula to this, but the simplest way to think about it is as you move away from a radiating object, an X-ray tube or a flashlight, the amount of intensity you experience goes down, okay? As distance goes up, intensity goes down. This is the inverse part of the inverse square law, okay? these radiographs are, at no specific distances, are showing you that if you look at image 1 through image 3, right? Image 1 was at one distance. It's got some, it's sort of overly black, right? It doesn't show it, bless you, it doesn't show any soft tissue. You go to image 2, and without changing anything else, in image 2, they just moved the X-ray tube away, moved it further away, okay? So image 2 will be less dense, less black, less dark, okay, brighter. Image 3 will be even less bright, okay, or sorry, even less dense, more bright, because we're even further away with image 3. So as we move the X-ray tube away, if we don't change anything else, the beam intensity at the image receptor decreases. Okay. So it's time to get a formula on the table. This is one of the important ones, so I'm going to spend a little bit of time on it. Okay. This is the inverse square law. The inverse square law says. So let's get the variables down. E represents exposure. So E means exposure. Do you guys all know what subscript is? Subscript and superscript. Subscript is below the variable. So like E with a little O to the bottom right of it, the O is a subscript. So I will say E sub O and E sub N. So E with a little O next to it is exposure old, O for old. E with a little N next to it is exposure new. So it's old exposure, new exposure. D is distance. And then N and O you already hopefully have figured out now, right? Distance new, D sub N. Distance old, D sub O. Okay? So let's read the formula. This is saying exposure old divided by exposure new is equal to distance new squared divided by distance old squared. Or old distance squared, whatever you want to say. I might, when I do this, exchange E for I, just intensity, right? It's the same thing, exposure, intensity. I'm going to use it, I'm going to leave it as E when I put it up on the board and write these out. But if I just, on a different day, if I just start to talk about the inverse square law, my brain will just revert to intensity. I'll use I instead of E because that's what I was taught. And I will use 1 and 2 instead of old and new. Okay, so like exposure old would be 1, E1, and E2 would be exposure new. So I will use different notations potentially, but the formula doesn't change, okay? What I want you to notice with this is, look at where the old and new is on the exposure side, and look at where the old and new is on the distance side. Notice they're flip-flopped, right? On the exposure side, old is on top, new is on the bottom, and on the distance side, new is on top, old is on the bottom. That's what makes this an inverse law, okay? If this were flipped, you would have a law that said, as distance went up, exposure also went up. Okay, we don't want that. We want an inverse square law. So make sure when you're writing this down, you get them flipped, right? EO over EN, DN over DO. Okay, you guys, it's gotta work with that. It's gotta happen. Okay. By the way, you can use anything. We can use anything we want for the exposure number. Okay. We could use actual units of radiation. We could say we could list it in units of gray, which is the unit of radiation we use. You know, some amount of milligray, right? We're not going to worry about that. For this first one, we're just going to use a literal just integer, the number 1 for exposure. Okay. So we're going to say the exposure old is 1. The exposure new, we're trying to figure out. That's the exposure at a new distance. And then we're going to have our old and new distances listed. Okay. Let's use let's use this here, and then I'll put one on the board in a second. Okay. So setting the formula up, they've told you that at a distance of 30, doesn't even matter what the 30 is, probably 30 centimeters. Again, doesn't matter the exact unit, okay? At a distance of 30 centimeters, the exposure is 1, okay? At a distance of 60 centimeters, we don't know what the exposure will be, okay? So the formula goes 1 over x equals 60 squared over 30 squared. Okay, so you've made it to here and you've set up the formula. They've given you your variables and you wrote down the formula based on the original formula that you knew, right? How do I go from there to here? What's my next step?
You do the squared.
I need to take care of the exponent, right? Remember, PEMDAS says takes care of anything that's inside parentheses, then exponents, then multiplication, division, addition, and subtraction, right? In that order, your order of operations. So 60 squared becomes 3,600, and 30 squared becomes 900. So 1 over x equals 3,600 divided by 900. Is everyone okay getting from the original formulation down to there? Take care of the exponents, get them out of the way, okay? Then what you're going to want to do from there is this step we call cross multiplying, okay? You'll take 1, multiply it by 900, and you'll take 3,600 and multiply it by x. So you get 3,600x equals 900. What are you trying to do? Like, what's the goal of this equation? Solve for x, right? And so in order to solve for x, what do you need to do? Yeah, you're a step ahead though. You need to get x by itself, right? Which means exactly what you're saying. You need to divide by 3,600 to get rid of that 3,600. In order to get rid of that 3,600, you're going to divide by that same number, right? So 3,600x divided by 3,600. Some of you are, by the way, some of you are fine with basic math. Some are not. I'm treating everyone as if we're not, okay? Because we might not be. So if you have to divide 3,600x by 3,600, then you need to do the same thing to the other side of the equation. That's what an equal sign means, right? Any operation you do on one side, you do the equal operation to the other side, okay? So 3,600x divided by 3,600 is x. That's that right there, okay? Then 900 divided by 3,600, plug it into your phone. By the way, 900 divided by 3,600 can be simplified. What can you simplify it down to? 9 divided by 36, right? Okay. So all you do, I don't know if I can do this very well because on the screen, but yeah, I can. Yeah, you just get rid of the zeros, right? If there's a 0 on the top and a 0 on the bottom in the same spot, get rid of it, okay? And there's 2 in this case, so you can make it 9 over 36, okay? I still can't necessarily in my head solve 9 over 36. You know, you might know that 9 goes into 36 4 times, okay? That would tell you it's 1/4, but don't worry so much about that. Just to take and get it on your phone, take 9 divided by 36, and it'll tell you the answer is 0.25, okay? So x equals 0.02, or sorry, 0.25, 0.25, 25%, 1/4, okay? So x equals 1/4, which is telling us the exposure nu at the longer distance is going to be 1/4 of whatever it was at the shorter distance, okay? Our exposure went down as our distance went up. The second distance, what's the relationship between the first and second distance? We had the first distance was 30, right? And the second distance was 60. They're doubled, right? Mm-hmm. So distance doubled. What happened to exposure when distance doubled? It went down by how much?
1/4.
1/4, or said another way, exposure went down 4 times, right? Exposure went down 4 times when distance doubled. That's the inverse square law, okay? At double the distance, you will get 1/4 of the intensity, not half, okay? Intuitively, you might go, if I double the distance, it'll be half as bright, right? It's not. It's 1/4 as bright. That's the square part of the inverse square law, okay? The inverse part is, as distance goes up, intensity goes down. The square part is, it's 1/4 as much if distance is doubled, okay? This would be a great time to ask a question, if you have it. Okay. So I'm gonna give us one to work with, okay? So we're gonna try one. We're gonna see if we can write it down. We're gonna see if we can all get an answer for it, and I'll work it through as you guys are writing it down. Okay.
Rick's got a question.
No.
lost it.
Go on, you're there, man.
I'm not there.
Enrique, I mean, if there's something I can help, I bet you if you've got a problem, I bet you someone else in this room has the same problem and it just wants to not look up and make eye contact with me. So, how can we help? This is, I mean, this is you're paying good money to come here. So is everyone else. What can we do? Is there anything? I mean, if it's everything, then we need to just, okay, so it's not everything. So if it's not everything, then it's something. There's something we can identify as the problem, right? So if you're having trouble, I can't help you if you just say, I don't understand, right?
Okay.
You have to say, I don't understand this thing. And then I go, oh, okay, I can fix that. And we can delve into that a little more.
So when I'm looking at these equations, and, the quiz, and there was a question on it, I'm looking at all the different principles, and I don't know. And I should use the, inverse square law, but I don't understand which principle to apply.
Like which formula to apply?
Yeah, like I'm not keying off of the information that's in it and going, oh, this is the inverse square, like you said.
Yeah.
Oh, this is the inverse square law. That's not happening.
Okay,
for me.
I think that's going to come
For a number
more.
of reasons, but-
That's going to come more from just practice, experience with the questions. But you have to look at what the question's asking you, right?
Right.
Typically, it's going to ask you something like, this next one will say, what is the exposure when distance changes, right? There's something that talks about exposure and distance, and that's the inverse square law, right? So you have to look at the context of the question, and try to apply
breaking
it.
it down. I think I don't know, if that's the big question mark on everybody's face, or at least from my perspective.
Okay.
I don't know which one to apply. So
All right, that's a harder question to answer. I'll
Yeah,
work on that.
not gonna make it easy.
So let's go ahead and work with this one here. Okay. So we're going to use a unit of radiation.
Useful. You might have to say that out.
So I want to use a unit of radiation for this next one. Okay, so this is in a few months we're going to go into a module called radiation safety or radiation protection, and we're going to need to get used to using units of radiation. Okay, so if we wanted to say an amount of radiation you gave your patient, we would use a unit called the milligray. Okay, a typical radiograph gives around 50 milligray. Okay, so we're going to say a patient received an exposure of 50 milligray at a distance of 80 centimeters. We want to know what would their exposure be, so it's an X, unknown, if the distance were 140 centimeters. Okay, so to set it up, right, let's just put the formula up here. So there's our inverse square formula, okay? And then the simple, by the way, Michael, you're usually told to use this formula. Using the inverse square law, give us an answer, right?
Mm-hmm.
In a lot of cases, you're told, use this formula,
Right.
I got questions on the homework which said, what formula do I use for this? And right above it, it said, use X formula to answer these questions, right? And so it might be a matter of just reading a little closer, looking at what it's actually asking you. In a lot of cases, it'll tell you what formula to use, but not always. All right, so then we'll just plug these in, right? By the way, when you're running this into the equation, you don't actually carry into the equation the actual unit of milligray. You can just leave it. So you just write 50 over x equals distance new is 140 squared over distance old 80 squared, okay? Now I don't keep these I think I keep that one logged in my brain, but I don't keep 140 squared logged in. So we're going to use a calculator, okay? You just take 140, multiply it by 140. That should be 6,400. 80 squared? Maybe check myself. Yay. If you do enough of these, you'll start to remember simple ones that are typically given to you. I got rid of the exponents by multiplying, right? 140 by 140, 80 by 80, 19,600 over 6,400, okay. Do I do anything to this side yet?
No.
So if I don't do anything to it, I just bring it down, right? I was really terrible about showing my work in math. I often skipped many steps, right? I want you guys to not skip steps. Why shouldn't you skip steps?
That's why we make mistakes.
You make a mistake, how do you know what your mistake was, right? That's when my math teachers would always get mad at me for. I'm like, oh, I don't want to make mistakes, right? I want to just get the right answer. They're like, no, you got to show your steps. That way we can figure out where your mistakes were. Okay, so I have this, right? What am I going to do with it? In order to find x, I'm going to cross multiply. Okay? I hesitate to say this, but there's also an alternative way of doing this called copy dot flip. Okay? Everyone remember copy dot flip from school?
No.
All right. If cross multiplying is difficult for you, so just look at this as 50 over x equals 19,600 over 6,400. And you want to know how to do this. Cross multiplying is one way. Copy dot flip is the alternative way, right? Copy dot flip says copy that, change that into a dot, okay, and flip that. All right? Copy dot flip.
Yeah, that's a different ground.
It's the same thing.
Yeah.
It's an identical operation. So watch. Copy 50 over x, a dot, what's the dot represent? Multiplication, and then flip. And then it's 50 times 6,400.
Which is 320,000.
Yeah, so it's just an alternative way of doing it. Okay.
I figured that out in my head.
Good. So you got 19,600 x equals whatever that comes out to.
Let's do it, figure that out.
50 times 6,400. Everyone okay getting to there?
Yeah.
Okay. So how do I get x by itself?
You move the nines.
So you can divide it by
600.
Divide by 19,600. Can I do it just to this side?
No, you have to do it to both sides.
Why?
Because that's the rules.
Because that's the rules we follow. Good. All right.
Smoking like
Whatever you
somebody's
do,
mama.
that's how you do it.
So I get x alone equals the answer to that, right? I can simplify this, but I don't have to. So just to be clear, I can get rid of that 0, that one, and that one. It becomes 3,200 over 196, which would give you the same answer as if you just divided it without simplifying.
So to get x alone,
Mhm.
you divide that number that's next to it.
Yeah, this one
And-
by itself.
Okay.
Yeah, because 19,600 divided by 19,600 is 1, right? So it'd be 1x or just x,
Oh, okay,
right?
okay.
Good. That's why we divide by itself to get. That's how we get rid of it, by turning it into a 1. And then the consequence of that is anything you do to one side, you got to do to the other, so you do it to the other side too. So 320,000-ish divided by 19,600.
16.326.
Only go to maybe the hundredth, the second decimal point. So x equals 16.32. So that's telling you that exposure nu,
You did that.
which is x,
No.
is 16.32 or whatever at that longer distance. Okay? At distance nu, 140 centimeters, our exposure was 16.32 milligray, whereas at distance 1, the exposure was 50 milligray. Okay? The exposure is the exposure at the longer distance, this new distance, is it higher or lower than the first exposure? The exposure at the new distance here, is this number bigger or smaller than that number? Smaller, right? Why was it smaller?
Because he's further away.
Because it was further away, right? The inverse square law says that as distance goes up, exposure goes down, okay? It's the inverse part of the inverse square law.
Milligray is the unit for the
Radiation.
radiation.
Yeah. Yep. Yeah. So just a unit. I won't tell you how to derive the unit right now, but it's just a unit. So okay, let's do another one.
standard.
Yeah. Do you? I'm still
That-
following. I get it.
Okay, so typical lumbar spine distance would be about 40 inches. Now we can just use a different unit now. We can go to inches now, okay? And a typical lumbar spine exposure, something around 150 milligray-ish, okay? And then we'll go to a new distance, all right? Let's say we didn't change anything, everything remained the same, but now we're gonna go to a distance of 72 inches, okay? Which is the other standard SID. So this would be correct, 40-inch distance and that much exposure, okay? That's sort of correct, all right? So now let's plug that in and let's see what happens. We have the unknown is X, exposure new. Oops. Sorry. Stalled out my brain for a second. 2 squared over 40 squared. And then it's just the same process, right? So you guys try working it through, see what we get. 6184? 72. Yeah, oh, 51. So 72 squared, 5184. 40 squared is 1600. 150 over x. Cross multiply. 1600 times 150. 240,000. 5184x. Divide by 5184. Divide by 5184. X equals the answer to that. Or it's actually 46.3. Okay. So, if you got something different, we'll figure out where we went wrong. So step 1 was to write it down. Step 2 is to write it down and then to get rid of the exponent. Step 2, we cross multiply. And at step 3, we do our division to get x by itself. And step 4 is our answer. So x equals 46.3, and the unit we started with was milligray. It's 46.29, round up to 46.3 if you want.
See, it's not too bad, I just feel like there's so many formulas and I just,
Yeah.
like, it's just.
Sort of a similar question that Michael had, like when do I apply the
Yeah.
formula, right?
Or like, once I see numbers, I get scared and I'm just like, okay, what the heck am I doing?
I don't know, for me it's like, it's the exact opposite. You give me a number, I have something to work with now, right? If I didn't have a number, then I'm just making up shit, right? If I have a number, I can plug it into a formula, and then I don't even need to use my brain. The formula does it for me, right? I just, my calculator and follow the steps for the formula, and I can't possibly get the wrong answer unless I took a step wrong. But you're right, when do you access which formula can be difficult, you know?
Or like, I forget what is what, or like.
Yeah, and in my next talk, we're gonna talk about something called the mass maintenance formula, which is the exact opposite of this formula, but looks almost the same. Okay,
Yeah.
it means that but you'll learn that the idea is to learn that they both are working with the same principle. Right? They're both working with the inverse square law. One's just telling you how the intensity changes at different distances. The other one would tell you, how do you maintain intensity when it changes at different distances, okay? So this is the first one to get on the table, the inverse square law. Okay, are we feeling okay-ish with this? Okay, able to plug it into the formula, able to work it through. Good, so let's move on.